Today's event is a part of popular lecture series supported by the Rustaveli National Science Foundation of Georgia and organized by Ilia State University. I'd like to extend special thanks to those people from Ilia State University who helped us in organizing this lecture series. And today's event in particular, let me just mention a few of them. Anna Khundadze, who is head of Research Coordination Office, and Vice Chancellor Anna Kvanchilashvili. The lecture today will last approximately 50 minutes. Then we shall have a small break, about 10 minutes, which will be followed by the discussion session. And now it's my great pleasure to introduce a well-known scientist, our special guest, Bharat Ratra. Bharat is a distinguished professor at Kansas State University. His scientific interests are related to cosmology and astrophysics. He received his PhD from Stanford University. After that, he held a few postdoctoral positions at Stanford Linear Accelerator Center, at Princeton University, at the California Institute of Technology and the Massachusetts Institute of Technology. And he later joined the faculty of Kansas State University. Please welcome our guest, Bharat Ratra.
Thank you very much. It's a great pleasure to be here. We got here very early on Friday morning, and I've seen part of the city, and it's very impressive. So I'm a cosmologist, and I study the structure and evolution of the universe. And it's a really interesting time to be doing this because we have some great new telescopes, both in space and on the ground, that are collecting great new data that are allowing us to study the universe much more in detail now. And they're reinforcing two really strong and interesting results. So you're probably familiar with one of them, that when you look out there and try to figure out what's contributing to the energy budget of the universe, we know that there are atoms and molecules, and that these are the things that we're made up of, and elephants are made up of, and blue whales are made up of, and the Earth and planets made up of. But when you add up all the atoms and molecules, you find that they only contribute about 5% of the energy that's driving the expansion of the universe. The remaining 95% is unknown, and it's got two really important parts. One's called dark matter, and one's called dark energy, and these are names for hypothetical substances. So we're seeing them because we believe in Einstein's theory of general relativity, and to make that theory consistent with the observations, we have to introduce these substances. And the other really interesting result we're seeing from these cosmological observations is that they're indicating that either quantum mechanics or Einstein's theory of relativity, or perhaps both, are incomplete descriptions of reality, and that they might need to be modified. And that would be very, very exciting, because for the last more than 100 years, quantum mechanics and general relativity and special relativity have been the foundations of all of physics. And so if those hold true, that would be really interesting, and we'd have to improve on general relativity and quantum mechanics. So I passed out some cards, and they're associated with this website, and if you didn't get them, I have some more here, and at the end you can come get them. So they're really interesting if you're interested in global warming. So I live in, oops, the clicker is not working, but I can use these guys, I guess. Nope. So I'm not sure how to advance. Okay, so I'll do that. So I live in Kansas, and this is a nature preserve about 10 minutes away from where I live, and it's a very nice place to hike. So I have some questions, and so you can answer them by putting your hands up. So how many of you gone hiking in your life? Okay, how many of you gone hiking 10 kilometers total in your life or more? 100 kilometers? 1,000 kilometers? Okay, so there's kind of an upper limit to which you can go. I guess if you have enough time and you have enough patience and you want to walk, maybe you can walk 10,000 kilometers in your life. Okay, so the next thing I want you to do is reach up and grab a strand of your hair and just feel the strand of your hair. Just feel it. So do you think your fingers are sensitive enough to feel something smaller or narrower than a hair, or is that the limit? Or I mean, that's kind of the limit, right? So if you have very sensitive fingers, you could probably feel something smaller than that, but it's kind of difficult to get down below that. So I have a bunch of length scales up here in meters, and if you are really, really patient, you can go 10 to the 5 meters or 10 to the 6 meters, but it's really difficult to access that, those length scales using your feet. And if you have very fine fingers, maybe you can get down to 10 to the minus 4 meters, but you can't access these scales directly through your senses. So the normal way you have of developing intuition, developing intuition over here is you use your senses directly. If you're very intelligent like Newton, you can collide marbles together, collide balls together, and figure out conservation of energy and momentum. And you can figure out the inverse square law of gravity by dropping things. But it's not the same over here, over here. So if you want to go to really large length scales and understand what reality looks like over there, you've got to use something like a telescope, and you collect light, and you send that light through CCDs, and that's turned into electronic signals that go into your computer, and that's all you know about what's happening over there. And so you end up building mathematical models of what you think reality is like over there, and you make predictions from those mathematical models, and you compare those predictions to these electronic signals in your computer. And if they look in reasonable agreement, you're pretty happy, and you try to improve your mathematical model in more detail. And down here, the same thing happens. Instead of telescopes, you use microscopes or particle accelerators, and again, you build mathematical models. And the way you develop intuition over here and the way you develop intuition over here is very different from the way you do it over here. And so maybe that's why people find it a little bit strange when you discover that quantum mechanics is relevant over here and relativity is relevant over here. And that's a little bit different than what happens over here, where things are mostly non-relativistic and they're mostly classical. And the physics over here is a little bit different than the physics over here. And it's kind of difficult to appreciate really this huge set of length scales. I mean, you could go out this way, you could go down this way. So today I want to go out this way and talk about large length scales. And what I'm going to do is I'm going to start on a human length scale. You probably recognize this guy. And I could be doing this in terms of length scales. I could also be doing this in terms of masses or ages or time scales. And we don't have time to do all of that today. So what I'm going to do is focus on length scales. And instead of meters, I'm going to use Einsteins to measure length scales. So an Einstein is roughly 2 meters. So we're going to go from the human length scale, which is an Einstein, to this picture, which has only become possible in the last 60 or so years. It's a picture of Earth from space. And you can see Africa, and you can see Madagascar and the Indian Ocean. And if you want to get an idea of the scale here, what you could do is you could drill a tunnel from the North Pole to the South Pole and go and get 6.5 million Einsteins and put one Einstein at the bottom, put the next on his shoulders, and the next on his shoulders, and the next on his shoulders. And you'd need roughly 10 million Einsteins to go from a human scale to the size of a small planet. So this is a pretty huge step, even out to a planet here. So we can go another step out, which is, excuse me, the scale of our sun, the big star that bars pretty much everything that happens on Earth. And you could do the same thing. You could drill a hole through the polar diameter. And if you want, you can use Earths. And you'd need 100 Earths to stack them up, one on top of the other, to get the diameter of the sun. If you do this in terms of Einsteins, you'd need maybe 700 million Einsteins or so and pile them up one on top of the other to get from one end to the other. So it's a factor of almost 1 billion from a human scale. We could go out and look at the next biggest scale, which is the Earth's orbit around the sun. And it's approximately a circle. If you want to do this more accurately, it's an ellipse. But we can average that out over a year and use the average radius of that orbit as kind of the length scale of the Earth's orbit around the sun. And if you want to compare that to the size of the sun, you'd need to put 100 suns in a row to reach from the sun to the Earth's orbit. So it's another factor of 100. If you're doing this with Earths, you'd need 10,000 Earths from the sun to the Earth's orbit. So it's a pretty large distance. Excuse me. In terms of meters, it's 1.5 into 10 to the 11 meters, which is a very inconvenient number to use when you're talking about planets, because you don't want to be carrying around so many powers of 10. And so what people do when they're studying planets and solar systems and extrasolar systems is they introduce a new length scale, and they actually use 2 different length scales. So one length scale is what's known as the astronomical unit, and the abbreviation for that is the AU. And that's the radius of the Earth's orbit around the sun. You could also equally well use like some kind of time if you know how fast that object is moving. And the most convenient thing to do is to use the speed of light, because light has perfected cruise control. It always travels at exactly the same speed in vacuum, no matter what's happening. And that's a huge speed. It's 3 times 10 to the 8 meters per second. And I mean, if you want to think about that in terms of how far light would go, how long it would take to cover a foot, which is roughly this distance, that's 1 nanosecond. It's a billionth of a second. So it travels very, very fast. And so if you divide this distance by the speed of light, you get 500 seconds. So light takes 500 seconds to travel from the surface of the sun to the Earth. So if you look at the sun, and you should be really careful if you're doing that, and you need to use protective equipment, but if you look at the sun, and what you're seeing is not the sun the way it is right now. You're seeing it as it was 500 seconds ago in the past. And it's the same thing with any other object. When you look to your right and you look at your friend next to you, that friend's probably about 2 feet away. And that's roughly 2 billionths of a second away. You're not seeing your friend the way he or she is right now. You're seeing them in the past by a few billionths of a second. And we are not really sensitive to things on that time, those tiny time scales. So we assume we're looking at that person as they are right now. But when you're looking at large distances and you're looking at faraway objects like the sun, it becomes significant. You're seeing the sun the way it was 500 seconds ago in the past. So astronomers either talk about light travel time or use the AU as the length unit. And so sometimes they call this a light second, and we don't have to call it a light second. We can just call it a second because we know it's the light travel time. And the light travel time is 500 seconds from the sun to the Earth. So we can go out to the next star, to the sun, which is this star Proxima Centauri. And if you look at that distance from the Proxima Centauri star to the sun, it's about 10 to the 5 times further than the distance from Earth to the sun. And in terms of light travel time, it's 4 years. So when you look at Proxima Centauri, you're seeing it the way it was 4 years ago in the past. You're not seeing it the way it is right now. In terms of AUs, it's 200,000 AUs away. So again, it's starting to become pretty messy to even use AUs. And so what people who study collections of stars do is they introduce a new length scale. And that length scale is called the parsec. The abbreviation is the PC. It's the parsec here. And that's a little strange length scale. And it takes a little bit of work to appreciate what it means. So there's a cartoon over here trying to explain what a parsec is. And so what we're looking at is the Earth's orbit around the sun, and the radius of that orbit is 1 AU. And what we're going to do is we're going to take our observer and put her on a rocket and send her far, far away. And we're going to send her so far away that this distance, this huge distance, is going to subtend an angle of 1 arcsecond at her. So an arcsecond is a really, really tiny angle. If you go around a whole circle, it's 360 degrees. And you can split each degree into 60 arc minutes, and then you can split each arc minute into 60 arc seconds. So that's a tiny angle. It's about 1/200,000th of a whole circle. And so the observer has to be really, really far away if you want this huge distance, this huge linear distance here to subtend a tiny angular distance, angular scale at her. And then this distance from the sun to the observer is a parsec. That stands for a parallax of an arc second. And in terms of light years, it's pretty easy to convert. You can work this out. A parsec is 3 1/4 years or 3 1/4 light years. So if you go 1 parsec, you've traveled 3 1/4 light years, and so it's pretty easy to convert from parsecs to light years. So to put in a few more numbers here, we can look at the furthest humans have ever been, and that's to the moon. And the moon is about 4 × 10⁸ meters from us. In terms of light travel time, it's roughly 1 1/3 of a second. So when you're looking at the moon, you're looking at it the way it was 1 1/3 seconds ago in the past. Maybe we can characterize the size of the solar system in terms of Pluto's orbit around the sun. And Pluto's orbit is 40 times, the radius is 40 times larger than the Earth's orbit radius, or in terms of light travel time, it's 6 hours. So it takes 500 seconds, about 8 minutes for light to get from the sun to the Earth. It takes 6 hours for it to get to Pluto. Pluto is very, very far away. It's much further out. And if you looked at those New Horizon pictures from that NASA space mission, those pictures were sent back as electromagnetic signals. And they took 6 hours to come to the Deep Space Network telescopes on Earth, and that's the distance Pluto is from us. The furthest we sent anything excuse me, are the 2 Voyager missions. They were launched in 1977, and in 2017, it had been 40 years since Voyager had been launched. And those numbers I put up there are from 2017. So at that point, Voyager 1 had gone 140 AUs from the Earth, roughly 3.5 times as far away as Pluto is. And in terms of light travel time, it's about 19 1/3 of an hour. And that's the furthest we've ever sent anything. So it's a really tiny distance. It's about 1,000th of a parsec, 1,000th of the distance to the nearest star, and it's taken 40 years to get there. So that gives you some idea of the scale even of the solar system. And the solar system is pretty tiny. It's just one star and a bunch of planets. And maybe I don't know if we can turn these lights down in front. Is that possible? Or is there some way to... Okay, well, I mean, you can go look at this picture on the web. It's called the European Space Observatory, or the European Southern Observatory, ESO, Milky Way. This is the big galaxy we live in. And I mean, it's probably easier to see this in an artist's impression. I'll just go to that. But it's a really beautiful picture when you look at it on the web. And you can try to, okay, let's just a minute go back to this and see. So this is our Milky Way. We're inside looking out. And it's a collection of stars. It's probably about 200 billion stars. And this is the European Southern Observatory Milky Way, and they have this in all kinds of different wavelengths, and you can see this on the web. Just look for ESO Milky Way on Google. And if you're using Google, just kind of go to reputable sites. If you can find a lot of crazy stuff on the web. Excuse me. So this is an artist's impression of the Milky Way. It's roughly a disk. So if you're looking at it from the top, it's like a frisbee. And the famous spiral arms, you can see it when you're looking at it from above or from below. And this is looking at it from the side. And this is the center. So this is the scale of the shiny stuff is, well, I guess that's kind of dropped 50. Maybe I can see if I can get rid of this top thing over here. You can't see the, okay, well, I'll read the number to you. So it's the scale here, oops, maybe I shouldn't have done that. The scale here is 50 kiloparsecs, so kilo is 1,000. And if we want to convert that into light travel time, you just multiply the 50,000 by 3¼ years, and that's about 160,000 years. So if you could travel at the speed of light, and you started at one end of the shiny disk and tried to get to the other end, it would take you 160,000 years. And you can compare that number to the distance between the Sun and Proxima Centauri, which is roughly 4 years, or the distance between the Sun and the Earth, which is roughly 500 seconds. So this is a huge object. It's got a couple of 100 billion stars. And the typical star is like the Sun. The Sun is probably about twice as massive as the average star. But it's a huge object. These guys are all pulling on each other gravitationally, and they're orbiting in the disk. And in the bulge region, they're moving around more randomly. They're not systematically orbiting as they're orbiting in the disk. So this is called the central bulge. There's a nucleus over here. And pretty much right at the center of our Milky Way, we have a big black hole. It's probably about 4 million times as heavy as the Sun. And on the scale of black holes at the center of galaxies, it's actually pretty small because many of them have black holes that are 1 billion times as heavy as the Sun. And there's a whole bunch of stars here. You can see these black bands. And these black bands are not telling you that there's an absence of stars. What they're telling you is that there's a lot of dust there. And the starlight is being absorbed or scattered by this dust. And so it's not reaching us. And so we don't see the stars that are embedded in the dust. But because that dust is absorbing light, it's getting hot, it's heating up, it's absorbing energy. That dust has to eventually either explode or it's got to emit that light somehow. And a lot of the times it does emit that light, and the light gets emitted at longer wavelengths. It gets emitted at infrared wavelengths. So if you looked at this galaxy or the Milky Way using an infrared telescope, you wouldn't see a black band here. What you'd actually see is really bright infrared emission. And so when you're looking at a galaxy, the wavelengths you use to look at that galaxy give you different shapes for the galaxy. You see it as a spiral with these big, beautiful bands. I'll show you that for another galaxy soon. But that image is only true for the visible light that you see with your eyes. So the Sun is roughly in the disk, and it's about 1/3 of the way away from the center. And there's also what's called a halo. That's maybe about 10 times as big as the shiny disk. And a lot of the dark matter is in that halo. And there are also these guys called globular clusters which live in that halo. These are collections of hundreds of thousands or maybe 500,000 stars. And they're distributed pretty spherically, symmetrically. And they tend to orbit this halo three-dimensionally. So this is a picture of our galaxy. We can look at other galaxies. And if you haven't seen the Milky Way, it's a really good thing to look at. You should be able to see it at certain times of the year. And it's useful to try to go take a look at it. You can also see this guy, if you haven't seen it. This is the Andromeda galaxy. It's the nearest big neighboring galaxy. It's also a spiral galaxy like the Milky Way, and we're seeing it from an angle from above. And this is the disk, and this is the bulge, and you can see the dust bands, and you can see the spiral arms of Andromeda. And Andromeda is a little bit bigger than the Milky Way, so it's about 60,000 parsecs in diameter, the disk of Andromeda. And that's about 200,000 years of travel at the speed of light. And we can't travel at the speed of light. It's only things that don't have any mass that can travel at the speed of light. And we can see a couple of interesting things around Andromeda. These are two dwarf galaxies, and they're orbiting Andromeda, just like the globular clusters orbit Andromeda and the globular clusters orbit the Milky Way. The Milky Way also has maybe 40 or so dwarf galaxies orbiting it. We can't see any from the northern hemisphere, but we can see two of them from the southern hemisphere, the large and small Magellanic Clouds. And Andromeda is 750 kiloparsecs from us. So that's a pretty large distance. In terms of light travel time, it's 2.5 million years away. So when you're looking at Andromeda, that light either was emitted by a star or a hot gas cloud, and it traveled in a straight line and came through your telescope and hit your lens in your eye and hit your retina, and got converted into electronic signal and got processed in your brain into this image. And what you're seeing is Andromeda 2.5 million years ago in the past, not the way it is right now. And that's an interesting time for the evolution of humans on Earth. One of the most famous human hominid fossils is Lucy, she was discovered in Ethiopia. And apparently she was trying to, she's about 3.25 million years old. She was apparently trying to escape from predators and climbed up in a tree and fell asleep or something and fell off and killed herself. But that's kind of the time scale. So Lucy's fossil is about 3.25 million years old. And the light you see from Andromeda now left Andromeda 2.5 million years ago. So this is one galaxy. It's got maybe 200 billion stars, and it's just one galaxy. There's many, many galaxies, and some galaxies are like people. They kind of collect together. Gravity pulls them together, and this is what's known as a cluster of galaxies. This is the Virgo cluster, and it's a relatively nearby cluster. Excuse me, and we're seeing the central region of Virgo here, and every single dot you see, these big ones and these little ones, they're all galaxies. So you're probably seeing maybe 1,000 or 1,500 galaxies here, even these little tiny dots here. And each of them have maybe 100 billion or 200 billion or 300 billion stars, typically the size of the sun. So this is a huge object. These galaxies are pulling on each other gravitationally, and they're orbiting each other. And the scale here is probably about 7 or 8 million light years. So if you travel at the speed of light, it takes you maybe 7 million years to cross this. So roughly 3 times the distance from Earth to the Andromeda galaxy, or if you're thinking about the light travel time across the Milky Way, that's 160,000 years. This is about 7 million years. And so it's pretty huge, but this is just one cluster. And there's many, many clusters of galaxies. And this is a picture. We can go back a second to look at our Milky Way galaxy. So there's this dust band here, and if you want to look out at the Milky Way and see what's outside, it's easier to look up where there's less dust. And so what I'm going to show you is a picture of the universe up here, and that's this guy over here. And we can't see the names up here, but this is by Shane and Virtanen. And that says Lick Observatory, which is an observatory in the San Francisco Bay Area in the mountains outside of San Jose. And this was done in the 60s and late 50s. And Shane and Virtanen, they would take these big glass plates with emulsion and put them at the focus of the telescope and then develop them. And so they looked at the sky and they looked at these galaxies. And then eventually by hand, they sat there and they figured out the positions of 400,000 galaxies by hand. This map was made in the 70s later using computers. Excuse me. But Shane and Virtanen didn't have access to laser scanners. They didn't have computers. And so they had to figure out the positions on the sky of these galaxies by hand using paper and pencil. So the scale here is about 300 million parsecs. So in terms of light travel time, you can multiply this by 300 million by 3 1/4, and that's roughly 1 billion years. So if you travel at the speed of light, it takes you 1 billion years to cross this. So this is a pretty substantial part of the universe. And the dots you're seeing here, so that dot is the Coma cluster of galaxies. And it's got maybe 6,000 galaxies, each of which has roughly 200 billion stars. And a typical star is like our sun. So that's a massive object, and it's just a few pixels on this map. You can see a lot of other clusters of galaxies. And if you look carefully, you can see three kinds of structures here. You can see these dark regions, and these guys are given a name. They're called voids. And they're dark not because the dust is absorbing light from these galaxies. They're dark because there are no bright galaxies in them. And if you look carefully, excuse me, you can see filaments, one-dimensional structures. So there's a lot of them. And there's also these clusters of galaxies. So the easy way to think about this is to think about bubbles in your bubble bath. And the bright galaxies tend to avoid the center of the bubbles. Those are the voids. And the bright galaxies tend to be on the surface of the bubbles. And where two bubbles intersect, you can get a one-dimensional structure there, and there's an enhancement in the number of bright galaxies. And those are the filaments. And where a bunch of filaments run together, where you have a bunch of bubbles coming together, that's where you get the bright clusters. So there's lots of bumpiness in this, and there's a technical name for this. It's called anisotropy. And maybe it's better to understand first what isotropy is. So when you're standing at one position and you're looking around you in all directions, above you, below you, in front of you, and to your right and to your left, when it looks the same, you say that's isotropic. And if you do that in this room, you can see that it's very, very anisotropic. You look to your right, you see someone. You look above you, you don't see someone. And so this room is very, very anisotropically distributed. And the same thing's true on the scale of the city or the country or even the surface of the earth. You look in some directions, you see mountains. You look in other directions, you see oceans. The solar system is anisotropic. You look in one direction, you see the sun. You look in other directions, you don't see an equally big star nearby. And Milky Way is anisotropic. You look in one direction, you see the center. You look in other directions, you don't see anything as bright. And this guy is also pretty anisotropic. You look over here, you see a bunch of voids. You look over here, you see a big cluster. You look here, you see another bunch of big clusters. The interesting thing that happens is if you go to a scale a little bit larger, to maybe a few billion light years, you see that it changes completely. And if this stuff wasn't here, what it would say is this is the the Planck satellite, so that was a European Space Agency satellite. This is a picture of the microwave background left over from the Big Bang. And it's the largest scale object we can see. So the way I'm displaying this to you is we're kind of sitting at one point in space, looking around in all directions at the surface that's inside. You can think of it as a big ball or something. And I sliced that from the North Pole to the South Pole and spread it out. So we do this also with the globe, the surface of the Earth. We spread it out. And we do the same thing here. So that's the North Galactic Pole, the South Galactic Pole. And you identify these two edges together, put them back together, and fold up the balloon around you. And we're looking at electromagnetic radiation that's come to us from every direction on that balloon. And we have blue hot spots and red cold spots. And from the color of this light, you can figure out the temperature of the light. And maybe the first thing you're interested in is the average across here, the average temperature. And if you average that across the whole surface, it turns out to be about 3 Kelvin. So the Kelvin scale of temperature is a scale that's kind of used in physics. And it's the absolute scale, so at 0 Kelvin, the only thing that's happening is you get quantum mechanical 0-point fluctuations. And as you go to larger and larger values of kelvins, it's getting hotter and hotter. So this room is roughly around 300 Kelvin. So when you say something's at 3 Kelvin, it's very, very cold. And once you have an average temperature, maybe the next thing you're interested in is to figure out how hot the blue is compared to the red. Excuse me. And if you do that, you find that it's about 30 millionth of a Kelvin different. So it's a really tiny difference. It's 30 millionth of a Kelvin relative to an absolute temperature of about 3 Kelvin. So if you do 30 times 10 to the 6 divided by 3, you get 10 to the minus 5. And that tells you the absolute bumpiness here. It's 1 part in 10 to the 5. Or in terms of percents, the difference between the blue hot spots and the red cold spots is 0.001%. So the temperature here is different from the temperature here, and it's different from the temperature here to 1,000th of a percent. It's a really, really tiny difference. If you go back here, it's much bumpier. You can see big differences between here and here. So these are two really, really important facts about the universe. One, when you look in your local neighborhood near you on small scales, and you look at how matter is distributed or how electromagnetic radiation or any other radiation is distributed, it's distributed in an anisotropic way in space. So it's spatially anisotropic. But when you get out to larger length scales, the distribution becomes isotropic. It looks the same in different directions. When you're looking at stuff nearby, it looks different in different directions. When you look at stuff far away, it looks the same no matter what direction you look in. And these are two really important facts about the universe. And I'm not really going to get into these much more, but if you're interested, the best explanation we have for this now is what's called the inflation model of the early universe. And you can read about that excuse me, by going to Google and looking maybe at Wikipedia and looking at cosmological inflation or cosmic inflation. You can also see this on Scientific American and other places, as long as you go to reputable websites. So those are two facts. I'm not going to get into them much more. This is another fact, and it's even more difficult to appreciate this one. It's that the universe expands. And when we say something's expanding, that automatically implies we have some kind of measuring device that can measure lengths, and that's not also expanding the same way. And so the first thing we want to do is try to understand what's going on with our measuring devices. So we could think of a meter stick, And a meter stick, there's two forces that are relevant for a meter stick. So we have 4 forces, but on the scale of a meter stick, there's a gravitational force. So if I don't support this and just let it go, it's got a mass, and the Earth's got a mass, and the Earth's going to pull it down because the Earth makes a gravitational field, and this guy also makes a gravitational field, and it pulls the Earth up towards it. So they both start moving together. But the Earth's much, much heavier, and so it hardly moves, and so you don't really notice it. But that's the gravitational force. So you have 2 masses, and you separate them by a distance. Let's call that distance r. And if you double that distance, the gravitational force goes down by a factor of 4. If you triple it, it goes down by a factor of 9. It's an inverse square law force. So the other force that's relevant on the scale of a meter stick is the electromagnetic force. And the electromagnetic force is also an inverse square law force. So when you double the distance, it changes by a factor of 4. You triple the distance, it changes by a factor of 9. But there's one difference between the gravitational force and the electromagnetic force. The gravitational force is always attractive. Things are pulled together. So the electromagnetic force can be attractive or it can be repulsive. So if you have the same charges, and there are 2 kinds of charges, there's positive charges, and an example of a positive charge is the proton. If you have 2 of them and you bring them close together, the electromagnetic force is going to push them apart. And you can have negative charges, so if you bring 2 electrons together, the electromagnetic force is going to push them apart. So if you have the same charges, the electromagnetic force pushes them apart. But if you bring a proton and an electron together, the electromagnetic force will pull them together. So you can pull stuff together if they have different charges, or you can push stuff away if they have the same charge with the electromagnetic force. For gravity, you can only pull stuff together. So we're made up of charged particles, right? So I have a bunch of questions for you. Are you pulling on your neighbor electromagnetically? So who thinks you are? Put your hands up. So 2 people think you are. And who thinks you're pushing on your neighbor electromagnetically? Okay, so most of you don't have an opinion? Okay, so that's correct. Like, you mostly don't push or pull on each other electromagnetically. And the reason for that is you're made up mostly of atoms and molecules, so we can kind of focus on atoms. So atoms have positive nucleus, and they have an equal negative charge around it with the electron cloud. So if you think about your electrons and your friend's nucleus, who's made up of protons, you're going to be pulling your friend's protons towards you using your electrons, and you're going to be pushing your friend's electrons away using your electrons. So on average, you don't interact electromagnetically with your neighbors. But if you kind of brushed your hair pretty vigorously and built up some static charge, you are pulling on your neighbor or pushing on your neighbor, depending on the charge of your neighbor relative to you. So what about gravity? Are you pushing each other away or pulling each other together with gravity? Okay, so you are pulling each other with gravity. So, but it's a really, really weak force, right? So your meter stick is held together by electromagnetism. And the way we get these numbers is you can look at 2 protons. They're being pushed apart electromagnetically, and they're being pulled together gravitationally. And so we can compare those 2 forces. And if you haven't done this, you should do this computation. And you'll find that the electromagnetic repulsion is 36 powers of 10 stronger than the gravitational attraction. So electromagnetism is an extremely strong force. But on scales of humans, it's not that relevant because we're made up of atoms, and atoms are neutral. And so the gravitational force is not getting screened, but the electromagnetic force is getting screened. And if you go up to the scale of stars, stars are also neutral. And so even though the electromagnetic force is much, much stronger, it's irrelevant on the scale of stars. and the gravitational force is much, much stronger because the stars have a much heavier mass. So as you go out to bigger and bigger scales, electromagnetism becomes less relevant than gravity. And on really large scales, gravity is the dominant force. And so if we want to talk about cosmology and we want to talk about the expansion of the universe, we need to talk about the best model we have for gravity, which is Einstein's theory of general relativity. And it's really difficult to understand this unless you do the math. And so what I'm going to tell you, I'm going to try to do this in words, but the words are just a translation from the solutions of the equations of general relativity. And so what Einstein does is he first started with special relativity. So Newton had his idea of physics where you had a fixed space and a uniform time, and you could collide balls in there, and you could figure out examples of conservation of energy, for example. And Einstein said, if you want to have a better description of reality, you can try to make space and time dynamical. So as these balls move, you kind of modify your space and time. And I'll tell you what happens when general relativity wanders around the universe. As general relativity wanders around the universe. Oh, can you just close that? Or I don't know if this... No. That's okay. Maybe you can just push it off. Let's see. Okay, great. So what happens is that general relativity wanders around in space, and where it sees less mass on average, it creates new space there. And that space has to go somewhere, and it spreads out. And that's the expansion of the universe. And that's very difficult to appreciate. So I'm going to try to show you some cartoons here, like demonstration cartoons. So I've got a one-dimensional expanding universe here. It's an exercise band, and I've got a wave on here. Yeah, maybe, I don't know if you put the light on. Excuse me. So you got a wave here, and you can see that it's got a wavelength, it's got peaks and troughs. And if the universe expands, you can see what happens to the wavelength. It gets bigger and bigger. And if it contracts, it gets smaller and smaller. So when we're talking about visible light, the short wavelength stuff is usually blue light, and the longer wavelength stuff is red light. So if you start out with short wavelength stuff where the peaks are closer together, then let the universe expand. That gets longer and longer, and it turns redder and redder. So you've got to think of your meter stick. Your meter stick is held together by the electromagnetic force, and the stretching here is done by the gravitational force. So this only happens in very, very large length scales. The meter stick does not get stretched by this. So gravity, I mean, this is not quite a very accurate description of what's going on. Gravity does not go to the ends of the universe and pull. So what it's doing, general relativity is going into space, and it's creating more space, and it's pushing things out. And it's also not doing this in one dimension. It does it in all three dimensions. So we live in a three-dimensional space here. So you can kind of see this if you think about, there's the vertical dimension and there's two horizontal dimensions. So it's a three-dimensional space. And this is happening in all dimensions. It's not just a one-dimensional expansion. So let's kind of move on to this, which is a description of what I just said, but it's a little bit more mathematical. So this is the universe at an earlier time. The exercise band is smaller. We've got a wave on it. That wave lives in the space. This is the space. It's a one-dimensional space. And the distance between two peaks is the wavelength. And as the band is stretched, the wavelength gets bigger. And so if you start out with blue light, it turns into more red light. It could turn into purple if you stretch it a little bit. If you stretch it a lot, it could turn into red. If you stretch it a lot more, it turns into infrared. And astronomers, they use this wavelength, and they prefer to kind of relate this to the size of the universe. So one way we have for the size, measuring the size of the universe, is to measure the distance between the two hands. And loosely, we can call that the scale factor. And the astronomers, or the cosmologists, give it the symbol A, and it's a function of time, so it's A of t. And as time goes on, as you go from an earlier time to a later time, t increases, and the size gets bigger, and the scale factor gets bigger. And cosmologists kind of use the scale factor, and it's pretty easy. I mean, you just take your elastic band, you draw your wave on it, and you take your meter stick, and you measure the wavelength. And you can see that the wavelength is going to grow in proportion to the size of your elastic band. And that's the red shifting. So astronomers don't use A, they prefer using something that's called Z or Z, the red shift. And that's defined this way: 1 plus Z is equal to the value of the scale factor at the present time, compared to the value of the scale factor in the past when that light was first emitted. And so in the past, the scale factor would be smaller than the value of the scale factor now. So this is a larger quantity divided by a smaller quantity, so it's going to be greater than 1. And the red shift then has to be greater than 0. So at the present time, A is going to be equal to A now. This right-hand side is going to be 1, and Z is going to be 0. So the red shift is 0 at the present time, and as you go back, it gets higher and higher. And we can look at how this was discovered observationally. So this was discovered, the first evidence for this red shifting was discovered by Slipher, and he was working at Lowell Observatory with this telescope. So this is in the state of Arizona. It's in a town called Flagstaff in the southwest of the United States. It's just a little bit south of the Grand Canyon. It's about 70 or 80 kilometers south of the Grand Canyon. So if you've ever been to the Grand Canyon, you've been pretty close to this telescope. And if you go again, you can go to Lowell Observatory and get a tour of this telescope. So what Slipher did is he pointed this at distant galaxies, and he collected the light here, and he passed that light through diffraction gratings, broke it up into its spectrum, and he identified the atoms and the elements that were producing this light, and he compared the wavelengths that he was getting through this telescope to the wavelengths that he was producing from those atoms in the lab. And he found he was getting longer wavelengths here. They were redder than the light he was producing from the same atoms in his lab. And he did this in 1912, and he didn't really know what was happening. So there's two possible explanations of this. I mean, you're very familiar with this phenomena if you've ever listened to a siren of an ambulance or a fire engine go past you. And it's called the Doppler shift. So if the fire, that's for sound, and this is for light, but they're very similar effects. So as that fire engine comes towards you, the pitch goes up, and as it goes past you, the pitch goes down. And when the pitch is going up, the wavelength's going down. So if it's moving towards you, it becomes bluer and bluer. And as it goes past you, it becomes redder and redder. And this is the Doppler effect, and that's what Slipher was seeing, and we can talk a little bit more about this. But there's one possibility, is that there was a huge explosion somewhere near where Slipher was way back in the past, and everything was moving away from him, and then he would see a Doppler effect. But that's not what's happening. It's something much more interesting that's happening. And this is kind of another cartoon, so maybe we'll go back to first this. So these guys, these ping pong balls are my galaxies. And once you form the galaxies, the expansion of the universe doesn't change the size of the galaxies. What's changing is the space between the galaxies. It's getting bigger and bigger. But the galaxies themselves are not changing in size. And so we can look at a patch of the universe here. So this is a three-dimensional universe, unlike what I showed you with the exercise band. And it's three-dimensional because it's got one vertical axis and two horizontal axes here. And I've cut out a little bit of it. And it's pretty clear that this can only be a finite piece of it. It's not the whole universe. And the way you realize that is you go to the edge and you look out. So if you look out, it's going to be looking different than when you look into the cake. And so it wouldn't be isotropic. It wouldn't look the same in all directions. So if you want this three-dimensional universe to look anything like ours, you've got to extend it to infinity in all dimensions. And so you can imagine this as one little piece that I've cut out, and I'm showing it to you here, but it's really continuing to infinity in all three dimensions. And the way we can kind of think of this as being flat is to think about the top of this table. So it's very difficult to draw non-flat three-dimensional universes. So I want to start out with a flat two-dimensional universe, which is like the top of this table. And so if I go to the edge and look out, it'll look different than when I look in. So if you want a flat two-dimensional universe, it's got to go out to infinity in both dimensions. And so let's focus here on these galaxies, which are the chocolate chips. And we're going to put observers on them. So we'll put an observer on number 2 and ask her what she sees as the yeast rises. And she'll tell you she sees every galaxy move away from her. And you can do this the same thing with the observer on number 5 and ask him what he sees. And he'll tell you that he sees every galaxy move away from him. And because the galaxies are moving away, there's going to be the Doppler shift, and blue light's going to turn to red. And the fact that Slifer saw stuff turning red doesn't mean he's at the center of the universe where there was an explosion and one point, every point started moving away from that point. This is the more correct description. If I'm going the wrong way. Every point in space started moving away from every other point in space. And this is the expansion of the universe. So we can look at this on a curved two-dimensional universe, and I'll try this one here. So what I've got here is a balloon, and hopefully this will start filling up soon, if we can get this. So once it starts pumping, you can kind of see it filling up. So these galaxies are like my ping pong balls. They're not going to change in size. They're the little red pieces of paper I've stuck on here. And because they're not changing in size, they're pieces of paper and they're stuck on the balloon. So this balloon is an image of a two-dimensional universe. It's not flat, it's curved because it's got a curved surface over here. And you've got to think of yourself as a little ant, and all you can do is get a rocket and travel on the surface of this balloon. You can't go into the balloon, you can't come out of it. There's nothing inside, there's nothing outside. The only thing that you have is the surface of this balloon. So if you kind of think about what you're seeing when you're on this galaxy, you have your telescope over here, and you have a diffraction grating on it, and you're looking at light from this galaxy. So this light takes a finite amount of time to reach here, and as it's traveling to this galaxy and to your telescope, space is getting expanded, it's getting stretched. And so if you started out with blue light here, it'll get a little purple by the time it comes here. But if you go to a further away galaxy, it takes longer for that light to travel to you, and that light is going to be even more purple. And if you look at this further away galaxy, it takes longer for that light to get here, and it'll be redder. And if you go over here and look at a galaxy even further away and look at it, it takes much longer for that light to get here. and so it's even redder from this galaxy. And that's the expansion of the universe. And the more concrete establishment of this came from Hubble's work, which was a decade and a half after Slipher. So Slipher had this relatively small telescope. So Hubble got this bigger telescope. It's a 100-inch mirror. It's in the San Gabriel Mountains, Mount Wilson, that's just north of the Los Angeles basin in California. And he could actually see individual stars in these galaxies that Slipher had looked at, and he could resolve them. And he realized he could find some very special stars in these galaxies, and these stars are called Cepheid variable stars because they pulsate. And they're very useful because of a relation that Henrietta Leavitt had found, I think in 1907 or maybe 1906. So Henrietta Leavitt worked at the Harvard-Smithsonian Center for Astrophysics just outside of Boston in Massachusetts. And that's where astronomers would send these glass plates with the emulsion after they developed them. They were basically the photographs they had taken. And astronomers tend to take pictures of the same region of the sky over and over again. So Henrietta Leavitt had 30 and 40 and 50 pictures of the same region of the sky. And she realized that she could see stars there that were pulsating, because in some of these pictures they were bright, and some of the pictures they were dim. And she realized that there were Cepheid variable stars, because people had known at that point that there were Cepheid variable stars. And she measured distances to nearby Cepheid variable stars, and she discovered a very interesting relation between the period and the wattage of these stars. It's called the period luminosity relation. And she realized that once she could measure the pulsation period, she would know how absolutely bright these stars were. And once you know the wattage of the star, you can use the inverse square law for radiation intensity. So as you go out further and further from the source, the radiation goes down like the second power of the distance from the source. And you can use that and Henrietta Leavitt's period luminosity relation to measure distances to these stars. So that's what Hubble did. He measured distances to these stars, which I'm calling R, in these galaxies that were pretty far away. And Slipher had measured how fast they were moving away by how redshifted they were. And so Hubble found this relation between the speed of recession and the distance to the galaxy. So a galaxy twice as far away would be moving twice as fast. A galaxy 3 times as far away would be moving 3 times as fast. And that's the Hubble law. And it's pretty easy if you think about this picture, that implies the Hubble law if you have uniform expansion. And maybe I'll just show you the data that supports the Hubble law, and then I'll stop here because I've run over the 50 minutes. So what we've plotted here is the speed at which these galaxies are moving away compared to the distance they are from us. And you can forget this bottom panel. Let's just focus on this upper panel. And these distances, the ticks correspond to the same points over here. So a galaxy 100 megaparsecs away is moving away at about 7,000 kilometers a second. A galaxy 200 megaparsecs away is moving away at about 14,000 kilometers a second when you go up over here. And this straight red line is the Hubble law, that the recession speed is proportional to the distance from that galaxy is from us. And I think I'd probably better stop here and we can have questions. And if people want, I can continue later.
Does anyone has a question?
I know that one possible interpretation of Hubble's expansion law is that the galaxies that are far away are moving faster because they are far away. Because if at the beginning they had different speeds, and when the expansion happened, the ones which we are faster, we are the farthest away. And this means that when they are far away because they are fast and not vice versa. And is this the correct interpretation, or somehow correct interpretation?
So maybe the way to say it is that every point starts moving away from every other point. It's not that there's one point and that you have an explosion, and some points, some of the particles start moving faster than the others. But it's every point moves away from every other point. And if you look at this, so you can see what you said. So the further away that galaxy is, the faster it's moving from us. So if you have a galaxy that's 100 megaparsecs away, it's only moving at about 7,000 kilometers a second if you look at this guy. And if you have one that's 200 megaparsecs away, it's moving at 14,000 kilometers a second. And so the further away they are, the faster they're moving. And that's not because they started out faster. It's just because that's what Hubble's law tells you. So if you think about this balloon again, if we switch this back on, so if you think of two nearby galaxies, they're going to only have a little bit of space created between them, and so they're going to move apart slower.
Yes, I am familiar with this concept.
Okay. Yeah, so the further apart they are, there's more room for more space to be created, and so they're moving faster from each other. But so I don't know if that answers your question or not, or
Yeah, it's quite correct.
Thanks.
Any other question?
It's just about curiosity. The huge distances and the smallest small that we now reach, the humans, are still our boundaries, what we can reach. So, and I'm curious, what are the maximums right now, and do we expect that still we have a very little understanding of real sizes and how big the sizes can go? I'm asking about the scale. For example, today's scale is like billions of light years, but it's still very big for us. But how it's from other perspective, how big this really is, for example, or what we compare it.
Okay, so there's a lot of things in your question. So the first thing I guess we should realize is that the universe has only been there for about 13.75 billion years. So we can measure the age of the universe, and it's roughly 13.75 billion years old. So if we kind of think of that time, the largest distance we could travel in that time, if we ignore the expansion, is 13.75 billion light years. And if we account for the expansion correctly, we can send a signal at the speed of light to about 30 billion light years. So that's the furthest we can see from us in the age of the universe. But as time goes on, the universe gets older and we can see more of it. And we don't know for sure what the shape of the universe is. We don't know if it's like this two-dimensional sphere or it's like the two-dimensional top of this table. The best model we have right now says it's like a flat universe, like the top of this table, except in 3 dimensions. And if that's true, then for it to be isotropic, it's got to go out to infinity in all dimensions. And so if we assume the simplest model is correct, then the universe is infinite, and all we can see is roughly 30 to 40 billion light years in any given direction. So we just see this really tiny fraction of an infinite universe, and we can't see beyond that. And the reason we can't see beyond that, you can see that in this law also, because this law is exact And this line, the straight line, just goes out to infinity. And so eventually you come to a distance at which a galaxy is moving away from us at the speed of light, and a galaxy further away is moving faster than the speed of light. So that doesn't contradict special relativity, and we can talk about that in a bit. But because there are galaxies out there that are moving away faster than the speed of light, the signals they send, the light signals they're sending, never reach us, and we don't see them. And that's called our horizon, and we can't see beyond that. And the fact that these galaxies are moving away, almost everything in the universe is moving away from us faster than the speed of light, and that doesn't contradict special relativity. Which, I mean, I can make things move faster than the speed of light pretty easily. So if I had a really bright green laser here, and you can kind of see, I don't know if you can see this dot. Yeah, you can see the dot up there, right? So I can move my hand really rapidly, and the red dot moves pretty fast there. So if I had a bright green laser and there were clouds, there are clouds above us now. On those clouds, that green dot would be moving very, very fast linearly. And if there were no clouds and the moon was above us, on the surface of the moon, that green dot would be moving faster than the speed of light. So we can make things move faster than the speed of light. What special relativity tells us is you cannot send a physical signal faster than the speed of light. And so for these galaxies, it's not that somebody strapped them to rocket ships and is sending them. So what's happening is space is being created, and that space is expanding, and the galaxies live in that space. And they can move faster than the speed of light without contradicting relativity. And that's why we can't see the whole universe, because at a large enough distance, these galaxies will be moving faster than the speed of light, and you can't get a signal from them.
One additional question.
Yeah.
Is the mass that we have in our galaxy is finite, or it changes?
In our galaxy?
Yes. What we have boundaries. We have like 13.5 billion of years.
You mean the whole universe?
Yes, the whole universe has some mass. It is teared apart. It goes away from imaginary center, and at some point, how can I say, reaches the point when it is 0,000 something in the space. The mass, I mean.
Yeah.
Yes, density, exactly.
Okay, so
density.
if you okay, so we're talking about the mass. So the mass is, if you believe the simplest model, the mass of the universe is infinite. So that makes life really difficult. And so what you want to talk about is the mass density. So it's the mass per unit volume, and you look at a little patch and you add up all the mass in there. And because of the expansion of the universe, the proper lengths are going to grow in proportional to the scale factor. And if you think about this guy, so over here, oh, sorry, I'm going the wrong way. So over here, it's a one-dimensional universe, and the scale is growing in proportion to the scale factor. If you go over here, it's a three-dimensional universe. And so you'll get expansion along this axis and along this axis and along this axis. And so the volume, which is the length cubed, so the volume is going to go with 3 parts of the scale factor in the denominator, because it's mass divided by volume, and you'll have length cubed. And so the densities are all going to drop. And so if you're just talking about non-relativistic particles, then you just add up all those particles in your box, and as time goes on, those guys will drop with the third part of the scale factor, and they'll eventually go to 0, and the density will become 0.
Any other questions?
So you mentioned that the space between the galaxies expands, but the space in the galaxies do not, like the galaxies do not expand. What might be the reason for that? Because the physical laws might be the same that are applied to these situations.
So when you're looking at galaxies and you want to think about gravity there, Newton's inverse square law of gravity is a very, very good approximation of what happens. And that's telling us that these galaxies are held together by this non-relativistic model of gravity. And you've got to get out to really large length scales where the universe becomes isotropic and homogeneous for you to be able to use Einstein's gravity. And that only starts, this expansion of the universe starts happening only on scales of tens to hundreds of megaparsecs, but on smaller scales. I mean, like this room is not expanding because your usual non-relativistic model of gravity is the dominant thing. So if you want to think about it in terms of this balloon is also not a very good approximation to what happens. So if you think about these nearby galaxies and you think of these in Newtonian terms, this guy is pulling on this guy is pulling on this guy, and they're pulling on each other with an inverse square law. So if they're close enough that R in the denominator of that force is small, and so the Newtonian pull is pretty dominant. But when you're talking about these galaxies over here, the Newtonian pull is pretty much irrelevant, and what's important is Einstein's description of general relativity. You create space, and that space creation process dominates over the Newtonian attraction. So on large scales, the space creation process dominates over the Newtonian attraction. On small scales, the Newtonian attraction dominates over the space creation process. And so if you want a more accurate model, these guys would actually be pulling each other together, and they're not going to be stuck on, they're going to be moving together. And that's just your Newtonian picture of gravity. So I don't know if that answers the question you had.
Any more questions?
When you say space creation, what does it actually mean? Because I think that it may contradict with the law of conservation of energy, because something can't be created from nothing, because space do have energy, as I know.
Yeah. So yeah, this is, I'm translating into words the solutions of the partial differential equations of general relativity. So energy is conserved, and so the way you can see that is from the equations of general relativity. So it's not a problem with energy conservation. And what's happening is that as the mass is getting diluted, as the density is going down, the gravitational field is also getting some energy, and so that's kind of playing up. And so you've got to account for the energy in the gravitational field, as also with the energy in the mass density. And when you add those all together, you can show that the energy is conserved. And so it's very difficult to talk about this in terms of words, but I just tried to translate into words what you get from those differential equations of general relativity. And that's the easiest thing to say, is that you're creating new space in regions where the mass density is low, and that space has to go somewhere, and it's spreading out, and it's taking the galaxies along for the ride. And because the gravitational field is also involved, the gravitational potential energy is compensating for the dilution in the matter energy density, but energy is conserved, and general relativity conserves energy in that sense locally. To discuss this globally is much more complicated, and we don't have a really good definition yet.
Okay, thank you.
Welcome.
Any more questions? I have a question.
Sure.
There was James Webb's telescope launched quite recently.
Yeah.
Maybe some new data from him that will shed more light on the properties of the universe.
Yeah. So there's already interesting data, but probably the most interesting thing. So if you look at these guys that are very far apart and see how the light propagates, they're going to propagate over a much bigger length scale in the universe. And so instead of just blue turning to red, the blue light can turn to infrared light. And the James Webb Telescope has infrared detectors on it. So infrared light is longer than the red you see with your eyes. And so you can see things further away with the James Webb Telescope. You can see things further away with infrared telescopes. And by looking at things further away, you're seeing them as they were earlier in time, because it takes longer. So if you think about this Hubble law, so when you're seeing things that are further away, it takes longer. So if you go from something that's 100 megaparsecs, it takes a certain amount of time for that light to get to you. And just like when you look at Proxima Centauri, it takes 4 years for that light to get to you. When you look at Andromeda, it takes 2.5 million years for that light to get to you. So when you look at something like 100 megaparsecs away, it takes a certain amount of time. But when you're looking at something 200 megaparsecs away, you're seeing that even earlier as the universe was expanding, even further back in the past. So when you go to further and further distances, you're going to earlier and earlier times in the universe. And because that light gets shifted into the infrared, the James Webb Telescope can see further back into the past than most of the detectors in the Hubble telescope. The Hubble also had infrared detectors, but most of it was in the visible part, the stuff you see with your eyes. But when you can see in the infrared, you can see further back in time and to larger distances. And so you'll be able to measure the Hubble law by going to further distances and get maybe a more precise estimate of the Hubble constant, which is the slope of this line. So that's one place it'll be really useful. It'll find really early galaxies and galaxies in the process of formation, and it'll tell us more about how galaxies formed. So hopefully we'll get lots and lots of great data from James Webb. There's another question back there.
Thank you for the presentation.
Thank you.
I have two questions. First is, so the angular momentum is the result of isotropy of the space in a closed system. But you said that on smaller scales, the isotropy, the space is anisotropic, but on a larger scale, it is isotropic. So does it mean that there might be a case when conservation of angular momentum is like broken, the law is broken? And second question is, if this, we know that speed of light is like finite, so like we see the star like 5 seconds later, like in the past. So if it was infinite, we would see it as it is right in that moment when we observe it?
Yes, if it was infinite, you'll see it instantaneously. And we know that it's not infinite because we can measure the speed of light, and you measured it very accurately. And so when you're looking at something, you're seeing it the way it was in the past. So the angular momentum, like in the simplest model of the universe, there's zero angular momentum total on very large scales. But when you come down to smaller and smaller scales, there's non-zero angular momentum. And even galaxies have non-zero angular momentum. And it's thought, and I mean, I think this is pretty much established. I mean, even though quantitatively we don't completely get exactly the correct numbers. But what's happening, so I guess there's no board here, but maybe I can say this in words. So gravity, so the universe expands, and there's a whole bunch of gas around there. So it's mostly hydrogen gas. And what gravity is going to do is going to start pulling this stuff in. And so you get clouds that form pretty much like you see clouds in the atmosphere. So there'll be a cloud over here and one over here. And they're not perfectly spherically symmetric. So if you have a cloud here that's not perfectly spherically symmetric and one here that's not perfectly spherically symmetric, you can kind of think, so it's not just that you have these clouds, but they have mass. And there's a gravitational force because you have particles in this cloud and particles in this cloud. And these guys are going to start pulling on this cloud. So if you just focus on this cloud, the nearby particles will pull much stronger over here than it'll pull on this end. And so this will start rotating, and this cloud will start rotating the other way. And this is called tidal torquing, and that's thought to be where galactic angular momentum comes from, that they pull on each other. And you can kind of develop this picture numerically, and you get roughly the right answer for the amount of galactic angular momentum that you see. So I don't know if that answers your question, but at small scales you get angular momentum.
In general, the angular momentum in general relativity is not necessarily conserved. For example, like if there is a if an object falls near the black hole and that black hole is rotating, so it has an angular momentum, that object's angular momentum is not conserved. Like if it just falls through the center, then it can gain angular momentum and fall into the spiral. So, problem correct.
Hi, once again. I have one more question. Will we ever be able to travel in another universes, or not exactly we, people in future, can they do that?
So that's kind of an interesting question, and I think you're talking about the multiverse.
Yes, kind of multiverse.
We can have, if you go back to this inflation model, you kind of nucleate lots of little bubbles, and they start expanding very, very fast. And eventually you lose contact with your neighboring bubble because the expansion's been so rapid, it's exponentially rapid. And the way we understand this now, we're not going to be able to talk to those other bubbles because they're too far away, they've expanded away from us. And I mean, maybe in the future, if we develop string theory or M theory and it turns out to be relevant, then we can actually go and calculate this and see whether we can talk with them. But right now it seems that we can't do that. And I mean, we don't really know how to answer the question you asked.
And what about teleport? Will it be ever able to teleport to one place to another?
Oh, so sorry, I didn't hear what you said. Did you say wormholes? Or?
No, teleport from one place to another.
Teleport, I don't think, I mean, at least, I mean, people try to build wormhole models and argue that that's one way you can travel much faster between things that are very far away in our space. But I don't know if that can be realized in the real universe.
And what about Bermuda Triangle? Do you believe in it and what is happening in there?
Sorry, I couldn't hear
the Bermuda Triangle.
The Bermuda Triangle?
Yes. Oh, I said it
so
wrong.
I
Sorry.
don't know if there's anything really going on there. I mean, I don't think that has much to do with cosmology. And maybe there's some issues with magnetic fields that kind of mess people's compasses up and mess the altitude on their planes. I mean, I don't know how significant that phenomenon actually is.
Okay,
that's not
thank
my
you.
area of work.
Thank you for your answers.
You're welcome.
Any other questions? Maybe Georgia, we can translate. No, calculate.
So, if you have no more questions, then let us thank our speaker. It was really exciting talk. On Monday, Bharat will give a seminar about more technical issues, right? If it's possible, our universe to have the special curvature and things like that. So, just applause to thank the speaker.
Thank you very much. I enjoyed my visit here, and I'm sure I'll enjoy the next few days. So if you have questions, I'll be around. I'll be happy to talk some more.